definition later on, and has developed from previous notions based on work by Winter and Kirchberg. And this is a joint work with Ilan Hirschberg and Gabor Szabo and Wilhelm Winter in particular, and Chanchao Wu. We also developed a dimension theory for dynamical systems, which is based in some sense on a refinement of the so-called Rocklin lemma, or that's the basic idea of that. And it has also the character of a dimension theory, and it has applications to nuclear dimension, which I want to discuss a bit. Okay, so let me start off with the introduction. As I said, it's an introduction to a non-commutative version of topological covering dimension, and it's geared towards nuclear C-star algebras and dynamical systems. And the basic idea of it is really to regard a completely positive approximation, an approximation of a nuclear C-star algebra, which exists for nuclear C-star algebras, as a sort of non-commutative partition of unity or some non-commutative open cover, and then to try to extend the definition of covering dimension to this setting using this sort of idea. And the corresponding dimension concept we obtain, they extend the classical covering dimension of locally compact and compact spaces, which due to Lebesgue and others, Czech from the 1920s and 1930s. I should say that this is not really, it's not a new idea to attach a dimension to non-commutative C-star algebras, but this approach has certain merits for the classification program. So for instance, one approach, and one earlier approach, is that of a stable rank of a C-star algebra, which is based on invertibility properties of density properties of the invertible group in a C-star algebra. But this sort of dimension theory is much less stable in the sense that if you take stabilization, if you take matrix algebras over your algebra, then you get a reduction of the stable rank. Okay, so let me, yes, and one word about the dynamical systems. As I said before, this is closely related to some sort of classical Rocklin lemma in ergodic theory. We'll discuss that later on. Okay, so let me start off with a covering dimension. This is a relatively old definition, about 100 years old, and probably not very well known. And I just want to recall the definition, and that will show us also why we define nuclear dimension the way we do. Okay, so we start off with a locally compact metrizable space, and we consider open covers of this space, and they're always finite open covers. And then we have the basic refinement relation between open covers, which says a cover U refines a cover V if every element in U lies under an element in V, right? This is the basic definition. Basically, it says that your refinement consists of smaller open sets. Okay, and then you can define covering dimension. This definition is due to Lebesgue, and then the version we use here due to Kolmogorov. That's from the 1920s. You say that the dimension of your space is smaller equal n if whenever you have a finite open cover V, then you will find a finite open refinement which is n plus 1 colorable. So it has certain partition properties. What does that mean? N plus 1 colorable means that you can decompose your cover into, you can partition it into n plus 1 families, and these n plus 1 families consist of disjoint collections of subsets. So they're pairwise disjoint sets. Any two are pairwise disjoint in there. Okay, and then you define the dimension to be equal to n if the dimension is bounded by n, but not bounded by n minus 1, of course. So that's the usual thing. You always define a dimension inequality, typically. Okay, and you can nicely illustrate that in the interval. If you haven't seen that before, I don't know. If you look at just the closed interval, then that better have dimension 1. And why does it have dimension 1 in this sense? Because you can refine every open cover, however wild it might be, you can refine it by a cover consisting of sufficiently short open intervals which have simple overlaps, right? Something like this here. Any open cover can be refined in this way. And this open cover you can certainly also color with two different colors. This is probably not very visible, but this would be the two coloring here of your open cover, okay? And that implies that the dimension is smaller equal 1, and it's certainly not strictly smaller than 1, so it's equal to 1 in this case. The usual definition uses multiplicities of covers. That's actually equivalent, at least for normal topological spaces, locally compact spaces. Okay, and this is the commutative definition, which has been around a long time. We want to generalize this definition to the class of nuclear C-star algebras to define the so-called nuclear dimension. Okay, nuclear dimension, let's start off with a brief reminder of nuclear C-star algebras that most of you probably know. So a C-star algebra is nuclear if the minimal and the maximal tensor product with any other C-star algebra is the same. So there's a unique C-star norm on the algebraic tensor product with any other C-star algebra. That's the original definition. For a long time, it was assumed that this is always the case, but it isn't always the case. There are non-nuclear C-star algebras. And there was a characterization of this class of C-star algebras from the 1970s based on work by Lanz, Choi, Effross, and Kirchberg that says that a C-star algebra is nuclear if it has a certain approximation property. Namely, there exists a so-called approximating net of triples. Here they are. The pointer doesn't work. So psi lambda, f lambda, phi lambda, and the usual picture or diagram you would draw there is always this. You have here your algebra, and you approximate the identity through these objects f lambda. Here you have your map psi lambda, and here you have your map phi lambda. Okay, and in this diagram, the f lambdas are finite dimensional C-star algebras. The psi lambdas and phi lambdas are completely positive maps, and you have that the compositions of these maps here approximate the identity pointwise. Okay, so you have that phi lambda circ psi lambda of A converges to A for all A in A. Okay, this is a completely positive approximation property. And these triples are called approximating triples, and the whole net is called an CP approximation. I want to point out that we actually only need to assume for nuclearity that the norms of psi lambda and phi lambdas are uniformly bounded. They don't have to be bounded by 1. We don't have to assume that they're contractions. This is something which we need actually later on for our definition of nuclear dimension. Okay, what has it got to do with open covers? How can we link that to open covers? It has something to do with open covers. An open cover actually, or a partition of unity, gives you a natural CP approximation. And that gives you a possibility to show that commutative C-star algebras are nuclear. I should stress that nuclear C-star algebras form a large class of C-star algebras, in particular containing all commutative C-star algebras. So how do we do that? Let's start as before. Let's prove that commutative C-star algebras are nuclear. So let X be as before. We want to show that Cx is nuclear. So let's take a finite open cover of X, and we choose a point in each of the open sets of our open cover, and then we can define a positive map from C0x into C to the U. And by C to the U, we really mean the tuples of complex numbers indexed by open sets in U. And what we do is we take our continuous function and evaluate it at these points xu. What we actually only need is probability measures supported in these open sets U. Okay, but point evaluations do. Okay, so then we get this positive map. And then we choose a partition of unity subordinated to our open cover. And we can define a second map from C to the U into the continuous functions on X simply by taking a tuple alpha u of complex numbers and forming this sum alpha u fu. That's certainly a positive map, completely positive because everything is commutative, and it gives us an approximation. This gives us CP approximation, the psi u, cu, phi u form CP approximation. This converges to the identity pointwise when we make u and finer and finer. Okay, so this is the natural CP approximation. It shows that commutative C-star algebras are nuclear. And the question is now, how can we read off the dimension of our space X from these triples? So we need a reformulation simply of the classical definition of dimension in terms of these approximating triples. That's the whole idea. Okay, and I should say this idea is really due to Wilhelm Winter. He came up with the first definitions of this based on this idea. And the definition has been optimized further and further. There was a definition of CP rank and then decomposition rank, and now nuclear dimension. Nuclear dimension is really a variation of previous definitions, but it applies to the biggest range of algebras, so to speak, optimized. Okay, so how do we do this now? How do we read off this dimension from these triples? Okay, suppose our cover U is n plus 1 colorable. So we have this partition into disjoint families of subsets. Then the key property is now, if we look at the second map, phi u, which goes from Cu into the algebra, it has a certain property. If you restrict it to C to the ui, then on C to the ui, it's orthogonality preserving. Because ui is a disjoint family, you can actually say that different components in C to the ui go to positive functions which are have disjoint supports. So it's disjointness preserving, orthogonality preserving. And that is really the property we're going to use. So what we have is a situation, if we define our finite dimensional algebra, if we have this finite dimensional Cu, we can decompose it here into C to the U0 up to C to the UN. That gives us a direct sum decomposition to certain algebras F0 up to Fn. And our phi u restricted to each of these summands here is orthogonality preserving. That is the property we're going to use. Now it becomes clear how we can generalize this to the non-commutative setting. This is basically the guide how to do this. Okay, so what we need is basically orthogonality preservingness. So the terminology used for this is, these maps are called order 0. They're called order 0. That is also Wilhelm's terminology. They're called order 0 because there's also the notion of order n map. Okay, but so far only order 0 maps have been important really. And well, orthogonality preserving might be a more descriptive name than order 0. But anyway, I think order 0 is now an established terminology. So what does it mean? Or just to formalize that, a map between C-star algebras is an order 0 map if it is completely positive and it preserves orthogonality of elements. So if you take any two elements such that x times y and y times x is equal to 0, then we should have that phi x times phi y is 0, and then also phi y times phi x. Okay, and these maps are, by the way, very close to homomorphisms. There is a result describing the structure of these. If you have an order 0 map between two C-star algebras, then you can actually write down a sort of internal Stein-Spring representation of that map. There exists then a homomorphism of A into the multiplier algebra of the range of your map. This maybe should be a closure there. And a positive element commuting with this range such that you can factorize the order 0 map in this way. This you can also write then as h to the half times pi a times h to the half as an internal Stein spring. Okay, so far so good. So now we can define, following the discussion in a commutative case, we can define our non-commutative dimension as follows. We can say a C-star algebra has nuclear dimension, again, smaller equal n, if you can find an approximating CP net, psi lambda, f lambda, phi lambda, where we assume that psi lambda is a contraction, phi lambda can have norm up to n plus 1. The next point will make that clearer why that can happen. Our f lambda should decompose into a direct sum of n plus 1 summons, and the restriction of phi lambda onto each summand should be an order 0 contraction. Right? If you assume that it's an order 0 contraction on each summand, then the norm can actually come up to n plus 1, right? Because we have these n plus 1 summands. Okay. And we define, of course, the nuclear dimension to be equal to n if it's smaller equal n, but not smaller equal n minus 1. Okay. And as I said before, there have been several preliminary definitions to this due to Winter and Kirchberg and Winter, and this one has the biggest range, and it makes the biggest number of nuclear C-star algebra finite dimensional. Okay, so far so good. Here are some basic properties which I like to list for this dimension. The nuclear dimension of a C-star algebra is 0 if and only if the algebra is AF. And the nuclear dimension really extends the dimension for the covering dimension for classical spaces. The nuclear dimension of C0x is the same as the covering dimension of x. That's what we want. And here's a nice feature. If you take a hereditary subalgebra of a C-star algebra, then the nuclear dimension only decreases. So that also implies that it's stable under Morita equivalence. And you have also a good behavior under taking quotients. The quotient of a quotient of an algebra can have only smaller nuclear dimension for every ideal, and the ideal itself also, because it's hereditary. And you have a good behavior under extensions. If you have an exact C-star sequence of C-star algebras, then the nuclear dimension of the term in the middle is bounded by the sum of the dimensions of the ideal and the quotient plus 1. And the behavior under inductive limits is also nice. Finally, you have a good behavior of tensor products, although you have a sort of funny bound here, which is not so nice. The nuclear dimension of a tensor product of two algebras is finite if at least the two factors have finite nuclear dimension. But this is maybe not the formula we would expect from the commutative case. It should be actually the sum, not this expression. Anyway, you can actually rewrite this here if you introduce nuclear dimension plus 1, this dim nuc plus 1, which means just you add 1, and you can dim nuc plus 1 of A tensor B is bounded by the product of the augmented dimensions. And the proof is trivial. You just take the tensor product of the approximations. But the bound is not so nice. Okay. Anyway, the most important thing is really that it's finite, because usually that is a condition which is important also in the classification of simple C-star algebras, just finiteness of nuclear dimension, not really what the value is. The values tend to be very small anyway for simple nuclear C-star algebras. So many simple nuclear C-star algebras turn out to have finite nuclear dimension. The values which occur are essentially only 1 and 0. Anyway, okay, let me just mention an example. So for instance, the behavior under inductive limits shows you that algebras like A theta have finite nuclear dimension, actually nuclear dimension 1, because you can write the irrational rotation algebras as AT algebras. They are AT algebras. They're inductive limit of matrix algebras over the circle. But you have another thing. For instance, the Toeplitz algebra has finite nuclear dimension. This wasn't the case for the forerunners of this dimension concept. So it's bounded by 2. It's actually not known what the exact value of this is at the moment. It could be 1 or 2. However, there are also some results about purely infinite algebras, which we proved in this article when we introduced this dimension. The nuclear dimension of the Kunz algebras is equal to 1, and for O infinity we had the estimate 2, and then for Kirchberg algebras we had an estimate 5 if they satisfy UCT. And the proofs were based on approximation techniques for Pimsner algebras. But in the meantime, more recently, various authors have actually shown that Kirchberg's algebras have a nuclear dimension 1, even without UCT assumption. Right, so the results are much stronger, which you have now. I want to mention another thing about the classification, the connection to classification on the next slide. Which is the background for that would be the so-called Thomas-Winter conjecture. So if you have a separable simple and nuclear C-star algebra, then it turns out that the condition that the nuclear dimension is finite of this algebra is more or less equivalent to classifiability. So one has, for instance, classification results for C-star algebras where Z stable, and the following conjecture makes a connection. It actually says essentially that the nuclear dimension being finite and Z stability are equivalent. So this is a conjecture from 2009. It has actually now largely been established. If you have a simple, a unital separable and simple C-star algebra, then the following conditions should be equivalent. A is Z absorbing, it absorbs the Yang-Su algebra. A has finite nuclear dimension. And then the third condition is a regularity condition for the Kunz semigroup, if you want. A has strict comparison of positive elements. So the comparison in the Kunz semigroup is determined by the traces, essentially. Okay, and as I said, these equivalences are essentially, well, established for a range of algebras, in any case for algebras with a trace, with a unique trace or with not too bad trace space. Anyway, this condition of having finite nuclear dimension is important in classification. Okay, one thing I want to quickly mention here is also nuclear dimension of row algebras. I don't want to define what row algebras are here. I just want to mention that because it contains the so-called asymptotic dimension of a space, and this will come up later again. Okay, so that's a result for about the nuclear dimension of row algebras. If you have a coarse space, then you can define a certain row algebra associated to that. So for instance, if you have a discrete group with a word length metric, then that's a very natural thing to do. And the row algebra in that case is also a certain cross product. And a coarse space, for a coarse space you can also define a dimension concept, which is more or less dual to the covering dimension of topological spaces. It's the dimension at infinity. You basically only dualize the dimension concept. You would then say, if you take a uniform cover of your coarse space, then you can find a coarser uniform cover, which is n+1 decomposable, n+1 colorable. It's exactly the same definition, it's only the other way around, so to speak. Okay, so this is how you would define asymptotic dimension. And what we can show is that the nuclear dimension of the row algebra is bounded by the asymptotic dimension of the space, so in particular finite for finite asymptotic dimension. Okay, contrary to that, I want to mention that much less is known for about upper bounds for the dimension of group C-star algebras. You cannot really infer anything from this. If you have a group, then the row algebra contains the group C-star algebra, but this doesn't really help you in order to get an estimate. It's not a hereditary subalgebra or something like that, so it doesn't give you a bound there for this. Okay, so far so good. I want to now say something about this dimension theory for dynamical systems. which is of a different character. It's, in some sense, you can also regard it as an approximation dimension. Okay, our original motivation for introducing this so-called Rocklin dimension is that we wanted to find conditions which would give us nice estimates for the nuclear dimension of cross products. That was really the motivation. And we noticed that the so-called Rocklin property, which had been studied for C-star dynamical systems, is very useful for that. Whereas in general, results for cross products are harder to get for general dynamical systems. Okay, I want to start just as a motivation with the classical Rocklin lemma, because part of what we do is also a sort of generalization of the Rocklin lemma to the realm of topological dynamics. So what does a classical Rocklin lemma say? That's due to Rocklin and Haltmosh. I think they proved that independently in the 1940s. It's something about transformations, measure-preserving transformations of a Lebesgue probability space. And it's about aperiodic ones. That is to say, the measure of the periodic points is 0. That's a null set. You would have thought that for such a transformation, you cannot approximate it by periodic ones. But indeed, you can actually. There's a strong connection to periodic ones. It's so to speak, approximately periodic. So what does the theorem say? It tells you that whenever you choose an epsilon, and you choose a natural number, positive integer, then you can find a certain subset of your space such that when you apply your transformation to it, you get disjoint subsets, and the union of these disjoint subsets almost fills the space up to epsilon. Okay, so basically you have the picture that your space decomposes into a subset E here, and a tower, so to speak, formed by these by just applying the transformation. So you have TE here until you arrive at the top here, and the rest of your space consists just of a small bit here, which has measure less than epsilon, and the transformation simply acts as shifting. And the top here essentially has to go to the bottom. Just a small bit can go here, and a small bit from here can go there. So you can actually approximate your transformation in a very strong sense by a periodic one, by a periodic cyclic permutation of these in measure. The transformation can be approximated cyclic shifts in measure if you want. And there are several extensions of this to the setting, to a larger class of groups, so-called amenable monotilable groups. And they're also for Neumann algebraic versions of this result, where you use the L2 topology. Okay, C-star versions of this, however, they should involve the norm topology. And let me just recall the definition of that. It was introduced, I think, in the 90s by authors like Kishimoto and Bartelli and Elliott, Evans, so on. So for finite groups, what is the Rocklin property for finite groups? If you have a finite group, then an action of this group on a C-star algebra has the Rocklin property if whenever you have a positive epsilon and you have a finite subset of your coefficient algebra, then you can find a tower of projections, pairwise orthogonal projections PG, indexed by this group. It's a finite group, so, and they should sum to 1. This tower should sum to 1, and the action of your group is approximately just the shift on these projections, regular representation, and the projection, the tower, should commute with your finite subset, and yeah, that's basically it. So you have, so to speak, an approximately central tower of projection you can choose for a given finite set. For each finite set and each epsilon, you can find such a tower. Okay, right, and the version for single automorphisms is that you say that an automorphism has a cyclic Rocklin property if whenever you have a positive integer, epsilon bigger than 0, and a finite subset, then you can find a tower of projections p naught up to Pn minus 1, summing to 1, and again you have approximate shift, cyclic shift on these projections. So alpha pi is essentially pi plus 1, where the index I is taken modulo n, and you have this approximate commutation. It's approximately central. You can choose that. Okay, and we noticed actually that this property is good for a nuclear dimension. If your algebra A has nuclear dimension, finite nuclear dimension, and you have a Rocklin action of a finite group or of the group Z, then it gives you good estimates for the nuclear dimension of a cross product. The main drawback is that this requires a lot of projections in your coefficient algebra, so the applications are very restricted. Okay, so what our idea was to extend this to the so-called positive Rocklin property. The definition for Z we came up with is here. If you have an automorphism, then it has the positive Rocklin property with a Rocklin dimension D, which is defined as follows. So if, that's the case, if for any integer, any finite subset, and any positive epsilon, you can now find positive elements, FLI, they have double indices here. This L counts the number of towers, which we are looking at, from 0 to D, in other words, it goes. And the I is the index going from 0 to n minus 1. That is basically the index which is shifted by the automorphism. And we just have L, just have D plus 1 towers. Okay, and what are the properties? First of all, we want that within one tower, different elements are almost orthogonal. And the tower summed up all together should be almost 1, so we have a partition of unity, essentially. And we have that our algebra approximately commutes with a tower from this finite subset. And moreover, we have an approximate shift, cyclic shift on each tower. Okay, and the smallest d which we can choose in this condition, we define then as to be the Rocklin dimension of the action of Z in this case. Okay, and then the case d equal to 0 is simply the usual Rocklin property, because then you're positive. You have just one tower in that case, and because they're positive elements, almost orthogonal and sum up to 1, you must have projections. So you have the usual Rocklin property in this case. Okay, however, this is much more flexible and applies to a much larger class of coefficient algebras. I should also say that the same definition you can, of course, make for finite groups. It's even easier in that case, also than having several towers. Okay, let me point out what it means in the commutative case. Then we're looking at the continuous functions on a compact Hausdorff space, say, and then our automorphisms are always given by homeomorphisms of the space. And then we're talking about, basically then we're talking about a certain partition of unity of our space, where you can say this partition of unity can be decomposed into, so to speak, cyclic orbits of, well, functions which have pairwise disjoint supports, so to speak. Or if you take the supports of the functions, and then you get an open cover of your space, and you can basically decompose this cover into disjoint orbits, or, well, in an approximate way, at least, this is the case. And in order to formulate the approximate way, in order to do this, you need the algebra Cx in a sense. Okay, anyway. The result which we then got is that this Rocklin property, this sort of higher Rocklin property, is much more prevalent than one would think at first. If you have a minimal homeomorphism and X has finite covering dimension itself, then alpha t has automatically finite Rocklin dimension. And Szabo reproved this result in more generality. He only needed actually freeness of the action, and he proved also a more general result, namely he proved the same thing for Zm actions acting on finite dimensional spaces, with a suitable Rocklin property then reformulated. Rocklin tower, the towers have to be reformulated a bit. Okay, and this, in some sense, can be regarded as a topological version of the Rocklin lemma. If you have a free action on a finite dimensional space, then, okay, you don't have the literal translation of the Rocklin lemma, but you have some, in this sense, you have a certain Rocklin lemma. Okay, so far so good. What we get from this are good upper bounds for the nuclear dimension of cross products, acting, say, on unital C-star algebras. I should say you can also do this for non-unital ones if you just reformulate everything a little bit using central sequence algebras. And okay, what you get is you get that the nuclear dimension of a cross product by a finite group action with this Rocklin property, you can bound this nuclear dimension by Rocklin dimension of alpha times nuclear dimension of A, and for Z actions we get a bound with a factor 2 here. The nuclear dimension of the cross product is bounded by 2 times Rocklin dimension of alpha times nuclear dimension of A, augmented by 1 again. And then Szabo proof for Zm actions, this result here, the dimension of the cross product is bounded by 2 to the n times dimension of alpha, Rocklin dimension of alpha times nuclear dimension of A. Okay, and the question is how that could be extended to a larger class of groups. So this is all very nice. We have finite groups, we have Z to the M. We want to extend it to a bigger class of groups now, and that's something we did recently. So this is a Rocklin dimension concept for actions of residually finite groups. Okay, so what do we do there? We start with a countable residually finite group with a certain residually finite approximation, Gn. What does that mean? The Gn's are finite index subgroups such that the intersection of them is just E. Right? You can always assume them to be normal, actually. So a group is residually finite if such a family of subgroups exists. And it gives you actually an embedding of your group into a product of finite groups. This class of group is relatively large and natural. For instance, if you look at linear groups with integer coefficients, these are all residually finite because you can construct a family of a faithful family of homomorphisms to finite groups, just pass to ZP coefficients. Okay, and we can also define the concept of a Rocklin property, higher Rocklin property in Rocklin dimension for action of such groups. Okay, we say that an action G on A of such a group has the positive Rocklin property with Rocklin dimension smaller equal D if now for any Gn there in our residually finite approximation Gn, if for any Gn and every finite subset and every epsilon bigger than 0, we can find positive elements Fl indexed G bar. These G bars are simply cosets or classes in G mod Gn, and the L runs from 0 to D, of course, such that in each tower we have again this approximate orthogonality, and we have that the towers form a partition of unity up to epsilon and approximately commute with finite subsets, and finally alpha acts like a shift on that simply by taking, well, the usual action on the homogeneous space G mod Gn on this quotient. Okay, and then the smallest such D is called the Rocklin dimension of our action. And this is a notion which works quite well and gives us similar results for cross products as before. And as to say, we get estimates for the nuclear dimension of cross products using this notion. What comes in here, you see, is what we need is a replacement of this factor we had before, 2 to the m we had for cross products by Zm. What is this factor here in this case? We expect an extra factor, so to speak, to occur. And this factor is something like the asymptotic dimension of the group. In fact, it's not exactly that. It's the asymptotic dimension of the so-called box space of the group. So that's why this heading of box spaces comes up here. That's really in the upper bound for the nuclear dimension of the cross product. We have the box space, the asymptotic dimension of the box spaces appears. Okay, let me just quickly say what the box space is of a residually finite group. So if we have our residually finite group with approximation Gn as before, then the box space is defined to be the disjoint union of all these finite quotients, G mod Gn. We take the disjoint union, make it a disjoint. I should have written the union sign with a point about it. Okay, and we endow that with a metric as follows. We take the metric on each of these finite quotients, coming basically from the metric on G, coming, say, from a void length metric. And we want that the distances between these different finite quotients is large. So, for instance, we can require this here. The distance between any two should be bigger than the maximum of the diameters of each of them. Okay. Then we get the following estimate for the nuclear dimension of the cross product. The augmented nuclear dimension of the cross product is then bounded by asymptotic dimension of the box space times the Rocklin dimension times the nuclear dimension of A. So the factor which comes up here is actually this. This improves even the Zm result. We only need here, in other words, not 2 to the m, but m plus 1 is enough, in fact. Okay, so far so good. Which groups now have this property that you have finite asymptotic dimension of the box space? This question has not been considered before, as far as we know. It's certainly finite if you have a finite group, namely 0, or m if you have Zm. But what is it in general? Well, some background results. Let me just mention that Günther has proved that if you have a residually finite group, then this will be amenable if and only if the box space has the so-called property A. This is a generalization of amenability. And this lemma provides you with the possibility to produce non-property A spaces by finding residually finite groups that are not amenable. But anyway, you have this equivalence, and moreover, you know that finite asymptotic dimension implies property A. So in other words, that the box space of our residually finite group has finite asymptotic dimension means some sort of strong amenability. It's stronger than amenability for the group. It's not quite clear how else to characterize this. At the moment, there's not so much known apparently about these groups. However, what we can show is that if you have a group which is of polynomial growth, then this actually, and is finitely generated, then it actually satisfies this asymptotic dimension of the box space is finite. And then this we can use. So in particular, and you can express this in terms of the so-called Hirsch length of your group. And for this class, we also get a topological Rocklin lemma. If you have a free action of a finitely generated nilpotent group, which is essentially the same as polynomial growth, on a finite dimensional compact space, then actually the Rocklin dimension of this action is finite. You can find finitely many Rocklin towers for this. And in particular, the nuclear dimension of the cross product in this case is finite. So if this is also simple, this cross product, it will be classifiable. Okay. And I should also mention there's a connection to this, to some recent work by Günther, Willett, and Yu. They defined the so-called amenability dimension for actions of discrete groups on compact spaces. And we can find a certain inequality linking those two, where the asymptotic dimension of the box space comes up. So our dimension seems to be related to their dimension. I should also say that we actually use amenability dimension in our work in order to obtain this Rocklin lemma. Okay, but I think my time is up. Thank you very much for your attention. Questions?
sort of properties of the algebra, can you actually, could you in principle calculate actually just from a knowledge of the system?
Sorry, from which properties you could retain from.
Well, I'm interested in whether this is some sort of simplicial approximation to the algebra, and if so, what information do you get out of your approximation about the entire algebra?
Philosophically, that should be the case. That's right. I agree, but I couldn't really substantiate it any more than that. Yeah, I'm not sure. But this is, in a sense, the philosophy behind the whole approach. Yeah.
Questions? I have one question.
Sure.
I mean, you had those inequalities. I mean, for the relation between this dimensions, nuclear dimension for sequential products and so on. Do you actually, I mean, do you have examples when these are equalities? Because I mean, they were always, let's say, equal.
No, I wouldn't say so. No.
Okay.
I mean, actually,
just the estimate, and you don't know whether it's saturated.
In many cases, you have strict inequalities.
Yeah.
That is
whether there's an inequality in some cases, for some examples.
no, we don't. I mean.